So let's quickly review what we did last class. So for that very simple network, we learned how to write the mesh equations, how to choose the meshes and write the mesh equations. And of course this can be extended for any network. The primary idea is visually you identify what all loops are there in the system. Okay, you define a current through each one of these meshes, and the current through any element that is shared only by one mesh is the mesh current itself. The current through any element or any branch that is common to two meshes will be the difference between the two currents. And there are two things we'll follow. Convention wise, we'll say that clockwise direction is the direction of convention for currents, and we'll also say voltage drops are positive, right? If you have a voltage increase, that will give you a negative. You can follow other conventions, but it's just easy if everybody follows the same convention. Okay. So for this particular simple network consisting only of resistors and voltage sources, we defined these three loops. We wrote down the loop equations: loop 1, loop 2, loop 3. You go around the loop, write KVL, and you get three sets of equations. You build the matrix, okay, based on these three equations. Okay, and it is of the form R times an R matrix times the I vector is the V vector. R consists of resistances. Okay, depending on what kind of resistances you have. Santosh, close the door, don't let anybody else inside. You are the last guy, you're lucky. Okay, the diagonal entries for this are going to consist of positive entries consisting of what? Sum of all resistances in the mesh. Okay, the off diagonal entries will correspond to the shared element between this loop and between the loop for which you are writing KVL and the adjacent loop. Okay, so you get a symmetric matrix times the vector of variables which are the currents. This will be equal to a vector on the right hand side which will consist of all the independent voltage sources. Okay. Now if you happen to have a current source, an ideal current source in this circuit, okay, you will have a problem. This is analogous to what we had in the original case when we were writing nodal equations. We took an example where you have IC instead of the original resistor. So now you can define what is called a super mesh. Okay, you write down KVL for the super mesh and completely bypass the current source. So the difference between the currents, okay, if you apply nodal equation at either side of these two current sources, okay, will give you the extra equation that you need to deal with this particular system of equations to solve this network completely. Okay, any questions on mesh analysis? Okay. Now two last things. Number one, the question of why nodal analysis is more preferred is primarily because it's easier to write down the equations for nodal analysis even for non-planar networks. Okay, mesh analysis is very easy to write down for planar networks. And of course this can be extended to mesh analysis can be extended using for controlled sources and so on. We won't deal with that in this course. You can talk about modified mesh analysis. Okay, the next topic of discussion is going to be circuit theorems, and so what we decided was, okay, let's take the first theorem we dealt with was what was called substitution theorem. Okay, so we have a network N consisting of resistors, voltage sources and current sources. So resistors, linear resistors, independent voltage sources, independent current sources. Okay, and suppose I consider only one element R. Okay, I take one resistor out of this network. Okay, and I look at the voltage across it and the current through this. Okay, so that, let us say this was some VR and this current was some IR. We said we want to replace this resistor by something else, okay, which will still keep the system of equations intact for the rest of the network. Okay. What was that? What was that element? Okay. So first of all, let me write down the title for this. This is the substitution theorem. Okay. So we want to replace R with something else. Okay. And we looked at several possibilities. So the first one we want to try is to replace this with a current source. So how did we start off doing this? Anybody? We first noticed that if you actually have a loop like this, okay, consisting of two back-to-back current sources, okay, this current Ix will continue to flow in this direction only, and on these wires, if you connect this system, this back-to-back connected current sources to anything else, there will not be any current through those wires. So that is the first thing we noticed. Any doubts about this? Okay. Then what we said, we'll take this, okay, and if you actually go ahead and connect these back-to-back current sources here, so I am going to use back-to-back current sources of value IR, okay. What is the current here? 0, correct? We just said that. So the current through these wires is going to be 0. Next step, I am just going to redraw this network slightly differently. These are all ideal wires. So I am going to take this guy. What was the original current through the resistor? IR. Okay, that didn't change. Then the next step I am going to do, I am removing this. I am just redrawing it slightly differently. Okay. I have just redrawn the same network. What is the current through the resistor now? Also IR. So that has not changed. What is the current through this? This is still 0. Okay. I hope this is clear to everyone. I have not done anything except redraw these ideal wires with a different shape, and that is all. So now once I do this, I can go ahead and cut off these wires and nothing will change in the two halves of the network. Is that clear? Does it affect anything else inside the network N or for this resistor? No. Okay. Right now I am concentrating on this network N and nothing else will change. It preserves the same voltage VR and IR. Nothing else will change. Okay. Similarly, if I had taken this guy, okay, and I could have added two back-to-back voltage sources of value VR, okay, and nothing will change. Two back-to-back voltage sources of value VR is the same as a wire. Okay, there is no potential difference between the two ends. Okay. What is the potential difference here? VR. What is the potential difference here? VR. What is the potential difference here? 0. Okay. That means that if the potential difference is 0, I can actually short these two nodes and there should be no change to the rest of the network. Right? Everybody agrees with this? Okay. So I take the same network. Okay. Now since I have shorted it and these are all just ideal wires, I'm going to redraw it slightly differently. This is VR. This is the voltage source of value VR. Okay. This is the other portion. And what was the rest of the connection here? There was one more short here. These are all just wires. I'm just redrawing them differently. That's all. What is the current through this? 0. Okay. Does anything change does anything change if I actually cut this wire? Not at all. Okay. So it is clear that the resistor can be replaced with either a voltage source of value VR or a current source of value IR. Yes.
For the current source replacement.
Yes.
So suppose you have a network that has just one current source and one resistor.
Just one current source and one resistor. Okay.
That is circuit. So if we replace that resistor with the current source,
okay.
the current will flow, but you don't know the voltage, right?
Okay. He asked a good question. So he says, if this consisted of just a current source and a resistor, right? Let's say the network consisted of a current source and a resistor. So you are talking about this. So let us say, actually I'll draw it better. So in other words, it looks like this. This was the resistor R, right? And if you had to replace, so let's say what was this current source's value? I0, okay, and you have some voltage VR across this. IR is nothing but I0. So he says, what happens if I replace the resistor with a current source? What will be the value of the current source I replace it with? If you had any other resistances inside, you wouldn't, right? In this case, because it just happens to be just only one current source and one voltage source, it looks like you will lose that information, okay? But actually, so the thing is, you will see these kinds of cases even in the theorems we go forward with, right? When you see degenerate cases like just having a current source or just having a voltage source, today one of the couple of other theorems we are going to look at, okay? You will see the same case. If you try to apply those theorems to these degenerate cases, it will look like you are getting meaningless results, and we will see what it means, okay? We will quickly see what it means for that case also. Okay, that's actually a good question. And I'm sure you can think of the same thing if you have a voltage source, okay, and so the corresponding case, if you try to replace it with VR. Okay. Now, if you have this, okay, so you can replace it with either of these two, right? You can replace it with either of a voltage source or a current source of the appropriate value. So what I'll do is I'll state this substitution theorem in the following manner. Okay, any resistance R with voltage VR across it and current IR through it, okay, can be replaced by a voltage or current source, actually a voltage or current source of value VR or IR respectively, okay, without changing the without changing what? Without changing the rest of the network, okay, without affecting the rest of the network. Okay, Now two things. See, the substitution theorem as we have stated it right now says any resistance R. But does it have to be a resistance? Where have we used the property that it's a resistor? Let's go back. Okay. Where have we used the property that it's a resistor? We have not. Okay. So in reality, this substitution theorem is valid for any two-terminal element. Okay. We happen to choose the case of a resistor. It's valid for any two-terminal element. Okay. Any two-terminal element, we can have a current V, Vx and a, Ix through it, a current Ix through it and a voltage Vx across it. Okay. So this is really valid for any two-terminal element. Okay. So we'll modify that here. Okay. Okay. With one small caveat. What is this? Instead of a resistor, it was a voltage source or a current source. What would you do? So it turns out, if you had a voltage source, for example, in the network, okay, if this particular element that you are considering is actually a voltage source, this particular element was a voltage source, you could replace a voltage source with a current through it, you could replace it with a resistor, okay, but with one exception. Any idea what that exception could be? As long as, what is the property of a resistor? Linear characteristics, but that is not what we are interested in here. There is another property we are interested in, related to the voltage and the current.
Current is not
No. What is that? Somebody said this term. What is it? Passive. Right? A resistor is a passive element, whereas a voltage or current source, right, can be passive or active. Right? It can operate in either of these two modes. So you can replace a voltage or current source only if it is dissipating power. Okay, as long as it is dissipating power, okay, you can replace the voltage or the current source by a resistor. You can follow the same argument, right? So, okay, if you, instead of a resistor, if you had a current, positive current IR in the, some I in this direction flowing through a voltage source, for example, you can replace it by a resistor of value V by I, Vx by Ix. Any questions? And you can see why. Actually, you can draw up a very simple network, okay, and try to replace the voltage source with a, if you had to, let's say the voltage source is delivering power, what will it look like? And you had to replace it by a resistance. What kind of resistance will it be? It will be some kind of negative resistance, right? So you can write up, so you can draw up some of the simplest simplest networks you can think of and see if this is valid or not. If you try to replace a voltage source which is actually consuming, which is actually delivering power with a negative resistance, you can see what happens. You will find that it's not valid. Okay, the substitution theorem will not be valid at that time. Okay, so the substitution theorem, the reason, of course, it is fairly useful at times, but really importantly, we are going to use it to prove the next couple of theorems we are going to study. Okay, so let us say I had a network N. So it's linear, okay, it has resistors, but it has linear resistors, but also voltage and current sources inside. Independent, okay, voltage and current sources inside, and it is connected through two terminals, let's say 1 and 1 prime, to another network N1, okay, and this N1 could be anything. I am not putting any restrictions on N1, okay, I am not putting any restrictions on N1. Okay, in fact, I'll even add one more thing. I'll say it can also have control sources. Okay, this network N consists of resistors, independent voltage sources, independent current sources, as well as dependent sources. I am just going to put one restriction. Okay, these dependent sources, these control sources, the controlling variable is not part of N1. That is the restriction I am putting. Okay, so dependent sources in N do not depend on voltage or current in N1. Okay, that is the restriction I am pointing out. But I am not putting any restriction on N1. Okay, except for this. N1 can even have nonlinear elements. Okay, it doesn't have to consist only of resistors or whatever. Okay, so let us say this voltage was some Vx, and let us say this current was Ix. Okay. Now the question we are going to ask is slightly different from what we have done before. We want to find out what can I replace N by. Okay, now this is a different question. I want to replace N such that the state of N1 does not change. Okay, you see the question now? I'll write it down here. That is my question. I want to replace N with something, network N with something, such that the state of N1 does not change. How do I do that? Huh? You have something? A current source. Why is it a current source?
Because voltage can be anything as well.
But I do not want, if I do that, if I just put in a current source here, okay, I don't know that Vx will be the same. I can put in a current source of value Ix, but I do not know that Vx will be the same. Right? If I put in Vx here, I do not know that Ix will be the same. Okay? So the way to show this, the way to find out what kind of system I can use here to represent, to stand in place of V1. So there are two parts. What we are going to do is a two-part solution to this theorem. Okay. Now first of all, N1 is a two-terminal element. Okay, with Ix and Vx. So I can actually replace it by, okay, by let us say a current source of value Ix. I can do that. I already know I can do that. That's what the substitution theorem tells me. Okay. So first I am going to do this. I'm going to take N. So this is 1 and 1 prime. This is Ix. Okay. This is what I'm going to do first. Okay. Now, of course, N, as we know, includes resistors. Okay. Right now, let's consider the simplest case, right? Resistors, voltage source, and current sources. Now, because N is linear, okay, it consists of resistors. What can I apply to this network N? I can apply superposition. Okay, N, for the network N, I can apply superposition. Okay, so the way I am going to apply superposition is in a two-step process. First, I am going to excite N with all the voltage and current sources that were originally part of N, but I am going to set Ix to 0. Okay. The second part of the superposition, I am going to set all the internal voltage and current sources to 0 and set Ix, this current source value to Ix, the original Ix. Is that clear? Any questions on this? So I am going to apply superposition in two steps. First step, I am setting Ix to 0 and I am going to apply all of the internal voltage and current sources. The second step is going to be setting all of the internal voltage and current sources to 0 and apply Ix only. And a linear combination of these two will give me the steady state solution. Correct? For what? What will it give me the steady state solution for? For what this should be, what the relationship between this should be, this network and these voltage and current values. Okay, so let us quickly look at this. I will just redraw it slightly differently. So I am going to apply superposition. Okay. So I have N. What do I do here? I am going to set Ix to 0 in the first step. If I set Ix to 0, what happens to 1, 1 prime? Who said short? What does it mean? We have seen a few classes ago that and a current source with value I equal to 0 is the same as an open circuit. Okay. A voltage source of value 0 is a short circuit. Okay. So if you set Ix to 0, okay, this means that it's an open circuit. Okay. And for that case, okay, I am going to call that voltage Vx as Vx1. Okay, so that's the first case I am considering. Okay, what is Vx1? Vx1 is the open circuit voltage at 1, 1 prime. Okay. What is the next step? I'm sorry, I just modified this guy. Okay. So I do not want to change this guy. That's okay. So Ix equal to 0, V open circuit, Vx1. Okay. So this is R, voltage sources, current sources. Okay. So this Vx1 is the open circuit voltage. Can I find that out? I can find it out for any network. Okay, knowing this network, the values of all the resistances, the network topology, and the value of the voltage sources and current sources, I can find out what this open circuit voltage is. I just take these two terminals, I don't connect anything between them, find out the voltage across them. Okay. What is the next step? So I take the same network N, okay, and this is a nulled network. When I say nulled network, I mean this consists of resistances only, okay. All the voltage and current sources are set to 0. What does it mean when I set a voltage source to 0? I am going to short its two terminals. What does it mean when I set a current source to 0? I am going to open its two terminals. Okay, you remember this for the rest of your life. Okay, don't make this silly mistake of shorting a current source or opening a voltage source. And then what am I going to do here? I have this current source Ix. Okay. I'll call this voltage Vx2. What is Vx2? How do I find out Vx2? What will it depend on? So remember, now this network is purely linear. It has no voltage or current sources. It consists only of resistors. Across, that means across these two terminals 1 and 1 prime, okay, I can find out the equivalent resistance. Okay, I am going to call it RTH. Okay, the equivalent resistance can be found out between these two terminals 1 and 1 prime for this network. Okay, what is Vx2 now? Look at the directions. What is Vx2? Between 1 and 1 prime, the network only has a resistor RTH. Okay, what is the value of Vx2? Look at the direction of the current source. It's downwards. So Vx2 is minus Ix RTH. Okay. Again, one of the important things about solving circuits systematically is to keep track of signs also. Okay, depending on the directions of voltages and currents. Okay, so Vx2 is nothing but minus Ix RTH. Okay, and Vx1 I am going to call this VTH. Okay, so what is Vx? Is a linear combination of these two, is just a sum of these two. It's nothing but VTH minus Ix RTH. Okay, so this VTH is called, does anybody know this? I think some of you might already know this. What is VTH? What is it? It's called the Thevenin voltage. Has anybody heard of this? No? Okay, fine. I thought some of you might have. Okay, so VTH is called the Thevenin voltage. Okay, RTH is the Thevenin resistance. Thevenin. Okay, Thevenin. So if you had to replace this Vx equal to VTH minus Ix RTH, okay, if you had to represent this using a representative network for N, how would you do this? So I have my current source Ix, okay, this is Ix. I want a voltage Vx equal to this across it. How would you do it? I want Vx to be this. What would you connect to this? Okay, a voltage source. And what else? A resistance. So what is the value of the voltage source? What is the value of the resistance? RTH. Okay. So the network N can be replaced, okay, by just a simple series combination of the Thevenin voltage source and the Thevenin resistance. Okay, and this is called the Thevenin equivalent of N. Okay, and this, obviously, what have we used? We have used only superposition and the substitution theorem. Okay, so this the statement that any network consisting of linear resistors and independent voltage and current sources, it can be replaced by an equivalent combination, series combination of just two elements. Okay, one is the Thevenin voltage, the other is the Thevenin resistance. This is called Thevenin's theorem. Okay. Okay, and very often you will just see, hear people saying, oh, what is the Thevenin equivalent of this network, right? Or what is the Thevenin equivalent across these two nodes, and so on. Okay, any questions? Yes. Okay, so what happens if you have, okay, so two things. Number one, what happens if you have dependent sources inside N? What will happen? So far we only considered R, voltage source, current source. Suppose you have dependent sources in N, okay, that are dependent on other voltages and currents inside N. Is there a problem? There is no problem at all. Okay, because the way of finding out the Thevenin is very simple. Okay, all you are going to do is you are going to find out, set Ix to 0 and find out the open circuit voltage. If you have any dependent sources are inside N, okay, after considering those, you have to find out the open circuit voltage across 1, 1 prime. Okay, that is all. They might modify your open circuit voltage, they might cause your currents and voltages to change, but you will still need to find the open circuit voltage across 1 and 1 prime. Similarly, when you set all the independent voltage and current sources to 0, what will happen to the dependent sources inside? Obviously, they will be de-energized, okay, and you will again have to see, okay, we will probably do an example of that in class, okay, maybe next class we will do that, what happens, how you will find out RTH and VTH if you have dependent sources inside. Okay, any questions? What would you do with the dependent current source if the controlling variable is 0? You would open it just like an independent current source. Okay, if the depending variable was 0, you would set the current source to be an open circuit across its two terminals. If you have a dependent voltage source, whether it's a current controlled voltage source or a voltage controlled voltage source, if the controlling variable was 0, the value of the voltage is 0, which means it's a short circuit. Okay. Okay, so it's very straightforward to see that you can actually replace any network, any linear network consisting of these kinds of elements with a very simple combination of VTH and RTH. You will find that this is an extremely powerful and oft-used theorem or oft-used technique. Okay, but because you can imagine that this is very powerful. If you are not interested in any, you just have a very complicated network, but you are just taking two terminals outside and connecting it to something else. Okay, it is very easy to see that you only want to deal with this because you want to see what happens here. Okay, you want to see what happens here, and in the end all you will do is this. This is N1 and this is RTH, and you can figure out what happens inside N1 very easily. You don't have to solve for everything. Okay. Okay. Now, when we started off, we said, we want to replace N by something very simple. We know, there is some voltage Vx and Ix, right? Now, if you see what we did was we replaced N1 with Ix. There is no specific reason to replace N1 with Ix across terminals 1, 1 prime. We know that we could very well have replaced it with what? With a voltage source of value Vx. Correct? Because we saw, what does substitution theorem tell you? You can replace it either with a voltage source of Vx or a current source of value Ix. Okay, but not both obviously. What happens if you replace it with a voltage source? So let us say I put in Vx here, and this is N. What do I do now? What do I do now? I am going to apply superposition. Okay. I am going to consider two cases. In one case I set Vx equal to 0. Okay. In the other case I set Vx equal to Vx. In the first case, when I set Vx equal to 0, N is energized. Okay. N is nulled. Okay. And then what do? I add these two cases. What do I add? So this will give me Ix1, this will give me Ix2, and I am going to add this to get Ix. Okay. What do you think it will give me? Suppose I set Vx to 0. What does it mean? What is Vx equal to 0? It's a short circuit between 1 and 1 prime. Okay. So this first case, this I'll call this In, which is the short circuit current. Okay, between terminals 1 and 1 prime. What happens when you set Vx equal to Vx and null everything else? How do you find out Ix? Again, if I null everything else, I can find out the resistance. I'll call it Rn. So this will give me Rn. What is this Rn? It is the resistance across 1, 1 prime of the network N after all its sources have been nulled. Right? What is that? Note that that is the same as the RTH we found out earlier. Right? It has to be. It's the same network. Okay? For which you are finding out Rn. Okay? So what do you think Ix will be? In. Okay, so it will be the sum of these two. One of them is In. In the other case, in the second case, you have Vx and you have Rn. What is In? What is Ix2? Ix2 is minus Vx by Rn. Okay. So what kind of network gives me this equivalent? So I have Vx here. I have 1, 1 prime. I want to replace this network N by something simple which gives me these two, this equation, this relationship between Ix and Vx. What is that? In, what else? In parallel with Rn. Right? What does this equation tell you? If Vx was set to 0, Ix should be equal to In. Right? What does it mean when Vx is set to 0? This is a short circuit. Does that happen here? Yes, it does. Okay? If Vx was set to, if for any other voltage, Vx, what happens to the voltage across it? Part of In will flow through Rn, the other part will flow through the voltage source. Okay? And what will be the current through Rn? Vx by Rn in this direction, right? So the current Ix will be In minus Vx by Rn. So Vx by Rn will flow through the resistor in this manner. Okay? Okay. This is called the Norton equivalent circuit. This is often called Norton's theorem. Okay, this is called a Norton equivalent circuit. In is called the Norton current. Okay, and Rn is called the Norton resistance. Okay, obviously the Thevenin equivalent and the Norton equivalent can, either of these two equivalent circuits can be used to represent this network N. Okay, both of these are equivalent ways of representing the network, and there is a relationship between these three quantities. What is that? What is the open circuit voltage here between 1 prime for the Norton circuit? What is the open circuit voltage here? Huh? It's In Rn. Okay, that has to represent the open circuit voltage for the original network N. What was that? VTH. VTH you calculated by finding out the open circuit voltage. Okay. Okay, this is the relationship between the Thevenin and Norton current and Thevenin voltage and Norton current. It is related through the RTH or Rn or whatever you want to call it. Okay. Okay, so let's stop here. I just want to ask you to think about one thing. If you had to think about one possible difference between the Thevenin and Norton, obviously as far as the network is concerned, voltages and currents are concerned, it's exactly the same. It has to be across terminals 1 and 1 prime. But there is a small difference between these two. Okay, you just draw, yeah, it's parallel and series, so of course they will be applicable in some cases, but there is one lingering difference. Okay, if you draw out the network, you can just look at write it down on a piece of paper, draw out the circuit Thevenin and Norton, maybe stare at it for some time, you might get it. I will explain it in the beginning of next class. Okay.